Well, hello. Good evening, Year 11s. Thanks for coming, guys. I've got a couple of people waiting. Cool. Okay, so I'm just checking that my stream is working. It seems like the audio seems to be up and running. If you guys wouldn't mind just sending me a message, just letting me know that it seems to be all functioning properly. I'm just trying to check to see whether or not if I can. I think that seems to be functioning now. Okay, right. So today I'm going to be doing a quick run through. I'm going to be doing a quick run through reactivity. This is going to be really useful because it takes a look at the behavior of metals in terms of acids, water, and salt solutions, and we're going to be looking at it in terms of redox. So I'm going to go straight. I'm going to go straight to my share screen, and then I should go to this, and you guys should now be able to see. Hi, Tiffany. Thanks for coming. I'm just going to quickly click play. I'm going to mute that. Also going to check to make sure that it is streaming at the quality that I want. I think it is. That's great. I'm just, yeah, that's perfect. We're there. Excellent. Hi, Tiffany. Right, just reminded some people. Oh, thanks, Tiffany. I do appreciate that. Okay, so you can see my title, and you can also see that I've prepared the reactivity series on the right-hand side of my screen. So today we're going to be looking at reactivity, and we're going to be doing kind of a crash course in less than an hour to look at all the various parts of reactivity for GCSE. And also, I'm going to do a quick exam question review as well to show you how this links in terms of the GCSE questions. So, learning objectives, we need to understand. We need to understand reactivity in terms of electrons in E- terms. We can then look at be able to describe reactions with, and I'm going to separate this into three sections. The first one, of course, I'm going to be doing it with oxygen. Each one of these I'll be relatively brief with. Then with water. Then with acid. And then the important one of these two. Hey, Julian, thanks for coming. Hey, Morella, it's nice to see you. Acid. And the last one, and I'm actually going to star this one. This is with salt solutions. Now, that's actually really important because at GCSE, the ones that are focused on primarily are this one and this one. They get looked at more often than the others in terms of reactivity. Water does make an appearance, but water, of course, tends to be focused on group 1 metals in particular. And that's, of course, linked directly with my first learning objective. But the other two, acids and salt solutions, are to do with this idea of comparative. This is reactivity comparisons. And they do this a lot. I don't want to put comparisons, let's put comparisons. And I've also got a couple of websites which are really useful for being able to show you guys it in terms of animations. And the last one, my last learning objective, which is really focusing now on the level 7, 8, and 9 questions, which is to understand reactivity in terms of redox. So understand redox and reactivity. So that's my aim today. And I could put this as a learning objective, and it's nice to do so, which is exam question review. Okay. Right. So let's go back to the beginning part of this in terms of electrons and the reactivity series. So I think the first thing that we can do is to try and define this term reactivity. And we have to look at this in two settings, reactivity. definition. We have to be really careful here because reactivity, of course, gets used. Oh, it's nice to see I've got Victoria on board. She actually made it. I think she's coming from the States, which is great. Hi, Sian. Nice to see you. So reactivity definition, you've got to be a little bit careful with, because there's two scenarios that we can place this in. We can either place this, I'm sorry, I'm just going to quickly, I'm very aware of my bandwidth on my internet, so I'm just turning down the internet on my second laptop. Okay, so we need to look at reactivity in terms of metals and non-metals. Now, this particular topic focuses primarily on metals rather than the non-metals. However, it's important to show the difference between the two of them. So in terms of metals, reactivity, the ability of a metal to lose electrons. So we can put that into an equation. So if we do magnesium metal, everybody recognizes a silver shiny metal. How Ping's made an appearance. What did I miss? I like it. You haven't missed much, How Ping. Learning objectives. Thanks, Tiffany. Filling in the gaps there for me on the chat. That's great. So the ability of a metal to lose electrons. Mg, magnesium, of course. We then go to my periodic table. Always have that guy on standby. Magnesium metal, of course, being in group 2, means it has 2 electrons in its outer shell. It's nice to see how atomic structure flows through all chemistry topics. And since it's got 2 electrons in its outer shell, it is going to lose them, and it's going to spit them out. So the definition of reactivity in terms of a metal is the ability of a metal to lose electrons. If we look at it in a non-metal setting, so this is nice to put underneath here, loss. In terms of the non-metal setting, non-metals, it's reversed. Non-metals, the ability of a non-metal, I'm just going to put non-metal to gain electrons. Let's look at an equation. So if I go to chlorine, Cl2. Now, the non-metals require a higher level of working here than the metals do. Because, of course, most of the non-metals that we're going to be using are traveling around diatomically, which means when they gain electrons, if we were looking at the particles, we would see chlorine in its diatomic situation, and each of those chlorines is going to gain 1 electron. We can even look at it from a Lewis dot and cross diagram. So we've got chlorine in its diatomic pair with the electrons in the gaps. So you can see that the chlorine atoms are sharing 1 electron. Now, this is not an ideal scenario. They would much prefer to gain their own electrons rather than sharing it, which means they're going to gain, and in this setting, it's going to gain 2 electrons because we're going to form 2 Cl minuses. Just to show you what's happening here is that the atoms are being split to become individuals. The atoms are being split. I shouldn't say that, it sounds wrong. The molecule is being split, and instead of having to share their electrons with each other, they will gain an electron, and you can see that there. This is the electron that's been gained. And the other guy, of course, will do exactly the same thing. It's nice, what I'm trying to represent here by putting them in that particular area. Students would often ask me, how do we need to know reactivity series? Do we need to know the reactivity series of non-metals? Good question, How Ping. The answer is yes, you do to a certain extent. You need to be able to look at group 7 in particular and recognize reactivity in that it decreases down the group due to their ability to gain electrons will decrease due to the outer shell being further away from the nucleus. So, but I'm just showing you it because I need you guys to recognize that it's not as easy as we would like it to be. We'd love to think of reactivity just in terms of metals, but as a chemistry teacher, I do have to make you guys aware that the non-metals, of course, also have a trend in reactivity, and that we can define that in terms of the gain of them. So, but in this particular setting for the reactivity series today, we're looking at metals primarily. So I can actually highlight this. This is what we're going to be focusing on today. We're going to be looking at how metals gain electrons and, how metals lose electrons and how their ability to do so changes depending on their position, atomic structure, etc., etc. So it's nice then, of course, at this stage, just to immediately bring in the understanding of redox. So redox and reactivity. So we learned, and at this point I'm going to do a little section on redox. Redox or redox, either one, I don't mind. Redox is when reduction and oxidation occur in the same reaction. Reduction and oxidation occur in the same reaction. Occur in same reaction. And we can look at redox in terms of, we can do oxygen. I'll put terms of. Oxygen, we can look at it in terms of electrons. That's all we need to do for GCSE. So we can say that oxidation, so oxidation is the gain of oxygen. The gain of oxygen. We can say that reduction is the loss of oxygen. We can also say in terms of electrons, oxidation, this is where I always at this point write in my words that I can't move away from, and I need to encourage you guys to do the same. This is a really nice fundamental acronym to latch onto. Oxidation, ox is loss of electrons. Loss of electrons, and reduction is the gain, of electrons. This is like a really useful thing, and then we can link it to our equations. So if then I go up to these equations up here, we can then say, so what we now realize is that the metals are losing. So metals tend to go through oxidation. So I'll put it over here, I'll change my color for this. If we're seeing electrons on this side of the equation, counts as the other side of the equation going in, this counts as red. So this is reduction is the gain. Red. I should have had the other colors, shouldn't I? Would have been more sensible. But it's nice to recognize that you can look at equations now and immediately identify whether or not oxidation and reduction is occurring. So if I had X gaining 2 electrons and becoming X2 minus, I go, that is going in, that is then therefore being gained, that is therefore being oxidation. So is and if we do the same thing, sorry, I always like to have things to look complete, the electron there being negative. If I had Y losing electrons to become Y positive, let's make it lose 2 electrons. And you realize that the charge that's being gained by your atom is directly linked to the number of electrons that you're having. Now, you do need to be very careful about this with the non-metals, because it's always nice to have rules, but there are always things that break those rules. Desperately. Pen. Because, of course, the example of chlorine reaction, laptop is having a hiccup. There we go. So in this setting, people would argue and say, well, chlorine has gained 2 electrons, so it should become 2 minus. This isn't the case, because I do have 2 minus over here. If you look at this in terms of their atoms, I have gained 2 minus ions. You remember, of course, this when we're doing atomic structure and atoms becoming ions, and how you get this, and I can even change the equation ever so slightly and go add 2e minus to show that those are the 2 electrons that are being gained, the circles there, or in this case, the dot and the cross in this case, that one and that one. Anyway, let's go back to our metals and start looking at this directly with our reactivity series. So now what we can do is, now that we can talk about reactivity for either metals or non-metals in terms of electrons, we can now start looking at this idea of comparative gaining and losing with multiple people. So if I was to choose two people from my table, if I was to say sodium and aluminium, what we can now say is that the more reactives, we recognize that metals gain electrons. Metals, did I say just gain? Metals lose electrons to form metal positive ions. They lose them, we know this, loss. And we can now say the more reactive a metal, the more reactive a metal, the easier it loses electrons. So we are focusing in now on the metal setting. We're ignoring our non-metals and their ability to gain. We're looking at metals and their ability to lose. So if I now look at my example I gave, we can now say sodium loses more easily, loses electrons. I'm tempted to say better. It's not a good word. Loses more easily is the way I want to teach that. Loses electrons more easily compared to aluminium. Loses electrons less easily compared to sodium. So you always realize that in order to define a metal's reactivity, we've got to compare it to somebody else. It's a funny thing that students often ask how you can place a metal in the reactivity series. And it's actually a really nice question. And this is where our reactions come in. Let's write that question down. Question. How, I'm very aware that I've zoomed in here. Actually, no, I'm going to stick with that. It's okay. Question. So how do you identify a metal's reactivity? Okay, so the first part to this answer is you must do reactions. You can't do it. Oh, I didn't mean to click that. I pressed it with my hand. You can't do it. You must do chemical reactions and compare it. Chemical reactions required. Chemical reactions needed. You can't, if I invented a metal, let's say I invented the metal titanium. Oh, I like that. That's my element, by the way. Chemical reactions needed. Let's look at titanium. So my element is going to be, oh, is there a TO on the periodic table? I don't need to actually open that periodic table up. I've got one up here. Is there a TO? I don't think there is a TO. I don't think so. So I can have that as my element. Let's call it titanium. I like it. Okay. So TO brackets titanium. Titanium. Okay, so I want to know where in the reactivity series, by the way, it's nice to define the reactivity series to boot because it does get asked. So let's just quickly do that. The reactivity series is a list of substances in order, notice my capitalization, in order of reactivity. Seems reasonable. Right, where does titanium fit in? So I've got a whole series of choices. So first thing, we can do the reaction with oxygen. So I'm going to go TO. So let's do reaction with oxygen. So I'm going to take TO. I'm going to heat it with O2, and I'm going to form TOO2. So I'm going to heat that. So what would this actually appear? What would it look like? This would be, I would have a pair of tongs. I would take some of my metal. I'd probably take a piece of ribbon of titanium. And I'm going to heat it up, and it's going to burn. It's going to burn. It's going to glow bright white. I'm going to get white smoke. The white smoke, of course, is going to be the titanium oxide. But the premise of this reaction is actually to recognize the inability to see where someone fits in. Because really, there's only two scenarios. The observations are either white flame, or bright white flame, either one, white smoke, and that's the first observation. That would be a bit like magnesium. The other observation, so this is if it did react. This is a yes to O2 reaction. The other observation is no change. We might see that there is a third option. If we look at an example like copper, it might turn black, or you might see a change on the surface change. Well, if there was no change at all, we could pretty much say low reactivity. Low, if not very low, either one. If it reacts on the surface, it is low or very low. You realize that there's a limitation to the reactions of oxygen. We learn at GCSE chemistry, we learn a couple of observations with oxidation reactions with metal, and the only one you really need is magnesium, the burning with a bright white flame. But it doesn't allow us to make distinctions and to make these observations as to how reactive something would be. So then we change our reaction, because then we go limitation of oxygen doesn't allow us to really see any real differences between metals. So at this point we go reactions with water. So reaction with water. Now, this reaction with water is a really nice one. And actually, GCSE students, this one's vital for you guys, because they like asking it, because it's a rather odd thing. It's not an easy reaction to kind of remember. I always struggled with this as a student. If I take titanium and I add it to H2O, what I'm going to make is titanium hydroxide and hydrogen gas. Now, if you're wondering how I'm building that formula, it was because of my oxide. My oxide that I created for titanium was TOO. What this means is, because oxygen has a 2- charge, if it's a 1-to-1 in that formula, it means that TO must be bringing +2. So I'm following that over in my water reaction. I'm going to balance it now. Going to need 2 oxygens, going to need 4 hydrogens. I think that now adds up. So it's nice for me to just reinforce for you guys reactions of metals and water. If you add a metal to water, metal plus water, what you're going to get is you're going to form the metal hydroxide and hydrogen. This is actually really, this is, again, level 7-8. Most students can't remember that one. It's not an easy thing to build, and it doesn't kind of immediately stand out to people. What they want to do is they want to swap the hydrogens for the TO and make TO. That's what they actually want to do. most students would do this, which is an error. They're going to form TOO and hydrogen. That's what they're going to do, and that's not correct. You don't form the oxide. You form the hydroxide in the presence of water. Oh, thank you, Sian. Sian, you're so useful. Thank you. You're a star. Hydroxide. Thank you. Metal hydroxide. I know. I caught it when Sian did it. I looked back. Thank you very much. So, yeah, you don't get the metal oxide with reactions with water. You form the metal hydroxides. Now, this reaction, I shouldn't really delete that. I don't see why there's any point in me doing that. This reaction is far more useful. Now, the reason why it's far more useful is the observation of hydrogen. Because if I was to put a selection of metals into water, what I'm going to see, the observation is going to be bubbles. The metal will slowly disappear, will slowly dissolve. I don't like the word dissolve. It's forming a new compound and dissolving into the water. But we're going to see bubbles. So here's what the observation is going to look like. We've got our beaker, we've got water in it. If we add our ribbon of tadonium, what we're going to see is we're going to see bubbles coming off the surface of my metal. Now, this is far easier to be able to have comparatively. Because if I now have a second metal, if I was to compare tadonium with, so this is tadonium and water, TO plus H2O goes to TO brackets OH2 and hydrogen. There's that one. If I take tadonium, and you can see the observation with the water there. Let's do cyanium. Cyanium is that's actually tricky because SI is already taken. Cyanium. Cyan, I've turned you into an element. Can't use S either. What are we going to have to use? We can use SY. It looks like an I. So cyanium plus water goes to cyanium hydroxide and hydrogen. Let's balance it. So I need a 2, and a 2. Right. Let's look at what cyan looked like in water. There we go. So we can now say comparatively that I'm more reactive. Tadonium is more reactive than cyanium. And it's simply due to the number of bubbles that we're observing. Yeah? Cyan is not happy that I turned her into a metal. She's not pleased with this. I hope you all realize either way that cyan also forms a +1 ion, whereas I'm forming a +2 ion. It's nice to see that as well. But it's the comparisons of the bubbles that allows us to compare its reactivity. So let's drop. So we can now say observations is bubble comparison. Now this is still not ideal. It's still not ideal. The reason being is if we drop a third metal in the mix, if we drop a third metal in here, let's drop a third metal into water. Let's do tifonium. Let's do tifonium. So TF, tifonium plus H2O goes to tifonium hydroxide plus hydrogen. Let's balance it. 3 oxygens, 6. That's going to give me 1.5 over there, which is a nightmare. So if I do one of that becomes 3, that becomes 6. That becomes 2 for the oxygens, and that becomes 2 there. I think that adds up. No, it doesn't. It doesn't, does it? Oh, no, it does. 12. Nice one. Right, so we've now got tifonium. Let's put tifonium into water. And what you'll realize is that tifonium is very similar to cyanium. And it would be very difficult. These two would now be much more difficult to separate in terms of their position in the reactivity table. We can definitely say that in terms of reactivity, most reactive, we can definitely position tadonium. That is easy. We can do most reactive is going to be TO. But then the problem is rank 2 and 3. It's either cyanium or tifonium. We don't really know which one's going to go where, because the bubbles produced in the water were very, very similar. So now we need a second reaction in order to make the decision. So now, what we need to now do, we have done, let's now do acids. Let's now change this for reactions with acids. Reaction with acid. Now, acids are a little bit more aggressive than water. The reason being, of course, is they produce large numbers of H+, and those H pluses are what are able to react with your metal. So we already know that tadonium ranks top. So let's just check this. Tadonium plus HCl is going to form tadonium chloride. And I was a 2+. And hydrogen gas. I'm going to see bubbles. Balance the equation. I can then do cyanium plus hydrochloric acid to form cyanium chloride. She was a 1+. Balance the equation. And then we've got tifonium reaction with hydrochloric acid to form tifonium chloride. Now this is far more, and that she was a 3+. And then we can balance the equation again. The problem is we're going to need common denominator. That I'm going to balance that with a 3, and that then gets a 1.5. And then I double everything. So that becomes 2. That becomes 6. That becomes 2. And that becomes 3 again. So 3. There we go. So if I now compare these guys, the observations are going to be pretty straightforward with me, with tadonium. So the 3 reactions are going to be a little bit more clear. And by the way, I know everyone is listening to this thinking I'm crazy, but actually they do this a lot at GCSE. They really do. We know that I'm going to be far more reactive. I'm actually going to be really quite vigorous. I'm going to have bubbles streaming off me rapidly. Cyanium again, it's going to be more reactive than it was in water, and then the tifonium once again. Now, it's difficult for us to be able to tell the difference between the latter two. Helping, LOL. Is a Mr. Duncan group 2? Yes. Self-awareness is the key. Yes, I'm group 2. Cyanium is group 1, but we don't know where in group 1. And tifonium's in group 3. So again, this one clearly is the most reactive, very obvious, violent bubbles. But these two are still difficult, still tough to separate. So now we can do a reaction which is absolutely going to tell us. What we're now going to do is metal and salt and metal plus metal salt reactions. Now, this one is now going to tell us who's the most reactive between cyanium and tifonium. Now, the reason why is because what we're doing is a displacement reaction. We're going to do a displacement. We're going to take cyanium and we're going to react it with tifonium chloride. And we're going to see if there's a reaction. We're going to take tifonium and react it with cyanium chloride. And what we're now going to do is look for any observations at all. So in this case, this one, observation, let's rather than giving the, well, what we can do is we can give the observation and then complete the equation as a result of that. Observation of these two reactions. So, bubbles and color change. No change. Right, so we can now determine from that particular reaction that cyanium is more reactive than tifonium, because there has been a reaction between the cyanium and the tifonium chloride that's going to form cyanium chloride and tifonium metal. So that's the observation I'm seeing. I'm more stable. Yes, you are more stable, Tiffany. You are. And then we balance the equation. We're going to need 3 of those to make 3 of those and 1 tifonium. Need a lot of cyanium for that reaction. But then this one, we saw no change at all. So it now definitively tells us which one is more reactive. Now, just to let you know, at this point, I'm very tempted to jump into both mentally and physically. Yes, I like it. Thanks, Jan. Now, at this point, I want to look at some GCSE questions. And there's actually one question I actually have that's particularly in my mind. And the annoying thing is, I actually don't have that question on hand. And I kind of need it. I can try and find something similar in the GCSE ones I've got, but I don't think I'm actually going to have the one that I need, because the one that I need is one that had a whole series of different letters. This is actually where I've let myself down by not having that question pre-prepared. I'm tempted to take one stab on the internet for this. I'm going to have one go at this, folks, and see if I can track this down. The question's going to be determine the reactivity. How to determine, experiment to determine the reactivity of metals X, Y, Z, and W. Let's go for that. I don't know where that's, I seem to have those letters in my head. Reactivity, let's change it to that. Let's get rid of W. It's whether or not this question is going to appear. And I've got a feeling that it's not going to. Let's try that one. The thing is, I actually want a very specific question here. Oh, is that the one that I want? No, it's giving me symbols. There was specifically one which, and they do this a lot at GCSE. I could start scrolling through GCSE papers, but I really don't want to. Oh, hang on a sec. I might have just spotted it. And I've just clicked something by accident, which I didn't want to do. I think I may have found it. Which is, it had 3 letters. No, that's the reactions with acid. You can see there, very straightforward, the diagrams that I'm drawing and how it relates. Oh, it's that one. It's kind of, maybe that one. Let's have a quick look at that one. No, it's not going to help me. I'm tempted to try and build it, but if I build it, I'm going to make a mess of it. I always do. I'm tempted to try and build it. Okay, anyway. I don't know whether or not it'll be on any of my other booklets. It might be on my other booklets. Okay, let's see if I can. I'm going to make one more effort to find this before I move on. Now the reason why I'm making this effort, folks, is because actually it's kind of worthwhile making this effort because it really does. It's one of those questions which students always find really tough. And I can understand why, I really do. Let's try book 2. And after this, I'll give up looking for it. And I will kind of, I'll have a stab at building it and make a real mess of it. In fact, one using temperature change, that's quite clever. Instead of using bubbles, they were looking at how high the temperature went. I think it's not there. How frustrating. Nope, that's annoying. I'm going to have a go at actually making one. Eek. So, X reacts with Y sulfate. Y reacts with Z sulfate. Z doesn't react with Q sulfate. Oh, well, I'll just put Z doesn't react with Q sulfate. Q reacts with Y sulfate. Put them in order of reactivity. That's what they like to do. They like to give you this series of bullet points of who's doing what and which reactions are where, and you have to put them in order. So what you do is you have to say, well, X reacts with Y. So X is clearly above Y. It has to be. Because X reacted with Y sulfate, which means it must be above it in reactivity. But then it says Y reacts with Z. Oh, so Y must be above Z. That means that Z must also be below X as well. And then it said Z doesn't react with Q sulfate. Oh, that means Q is more reactive than Z. So Q must go in somewhere here. Q is either here or here. Well, it then says Q reacts with Y sulfate. So Q is either going to go here or perhaps even there. It has 2 positions. Yes, absolutely. It could actually technically, they haven't told us whether or not it reacts with X, but that's going to be your 2 options. Does that make sense? It's nice for me to explain to you that was my effort at the GCSE, and they love these questions because students find them incredibly difficult. And it is just this. It's a purely logical process. Just put them down in this vertical order as you go through the question, and it will make sense, I swear to God. So it's worthwhile when you see this question, if you're confused at all, come and see me. Okay. So what we've now done is we've kind of covered reactivity in terms of salt solutions, acid, and water. Now what we need to, and oxygen, what we now need to do is we now need to look at them in terms of redox. So if I quickly go to this one, we can describe them there and say the limitations of oxygen. We can describe them with water forming their hydroxides, but lots of metals don't react with water, so relatively low in its usefulness. Acids are a bit more useful because they react with more metals compared to water, but in reality, the salt solutions are far better. And in fact, if they ask you to determine how reactive a metal is, you have to react it with the salt of the other metal. It is the only way to know with absolute clarity. It is the only way. And that question, again, I'm going to highlight that one. The salt solutions is so important. Okay, let's now look at this in terms of redox, because this now becomes a whole lot harder. Right, this now becomes level 7, level 8, level 9. So redox reactivity. Now, I have to do something now. I have to get you guys to understand redox reactivity specifically ties in with the salt reactions. Redox and reactivity is metal plus metal salt reactions. Now I'll explain why. And now I've actually found a rather lovely website. Let's see if I can find it. There we go. This is my lovely website. This is an introduction to chem from the OK State Education. I love that. It's actually OK. I can't remember where it stands for, but it's somewhere in America, I think. But this university put together a really nice animation to show you what's happening with metals in their aqueous solutions. So this is perfect. If anybody in this webinar thinks that they'd benefit from having a look at this website, you can have a quick search for this. Yeah, and the address is up there, which is intro.chem.okState.edu/1515F01/laboratory/activity of metals/home/.html. So let's have a look at what this is. Now, this is super useful because what it allows me to do is it allows me to kind of show you guys, what the salt solutions look like. Because I think students don't really realize this. This is magnesium nitrate. Because, and let's actually look at this now. So we've got metals. Let's have a look at what a metal looks like. So metals, of course, if we now zoom in, oh, look at my amazing diagrams. So if we look at this metal, what it is a series of metallic atoms, all in their beautiful layers. Let's do tadonium, tadonium. So this is my metal, and it's my metal atoms in their beautiful layers. The layers can slide. It's what makes them malleable. So if I look at the metal atoms, they're all there. And then if I look at what this looks like in terms of a salt solution, so that there is tadonium metal. Well, what does a salt solution look like? Let's compare this. Let's compare this to tadonium chloride. So let's go TO, and I'm group 2, so Tockel. And what does this now look like? Tadonium chloride, number 1, when it's in water, rather than floating around as ToCl2, what's actually happening is it breaks apart into its ions. This is what it looks like. And there's many of these, many tadoniums floating around, tadonium 2 pluses, and there's lots of Cl minuses floating around. So, and then it's nice to show the animation because there's the magnesium nitrate, the ions. Let's have a look at silver nitrate. The ions are kind of floating around in the solution. They're no longer together. This is because when something dissolves, the water pulls the ions apart. Now, this is really, really useful because what this means is, unlike the metal, which has its electrons, the ions don't have their electrons. If I go to dissolution of an ionic solid and I click animate, the water pulls those ions apart. and you see the negatives and the positives. If I just turn up the temperature, it'll just speed that up a bit. So the water, those ions are now free and flowing around. So now what we can do, so in terms of redox, if I add, now we've already determined from our previous experiment, we have already decided that of all three of my metals, tridonium, cyanium, and tifonium, tridonium is by far the most reactive. Well, I think we should confirm this. Think it's only fair. And let's look at it from a redox perspective. So, first thing is, from a redox perspective, which is all about, redox is about losing and gaining electrons. Gaining electrons. Let's remind ourselves, oil and Rig, oxidation, ox is loss, and reduction is gain. Right, now that we've got that clear, let's take tridonium metal. Let's take tridonium metal and add tridonium metal. We're going to add it to tifonium chloride. So what did tifonium chloride look like? Tifonium chloride was TFCl3. She was a 3+. So I add tifonium chloride to water, and the ions separate to form TF3+ and Cl-, Cl-, and Cl-. Right. Now, if we look at this as a simple metal salt equation, we've got tridonium plus tifonium chloride. Right. We already, as a group, as a class, we already know what the product is going to be. Year 11, year 10, on the chat, please. Who's going to get the commendation? What's my product of that reaction, please? We already know the answer because we discovered their reactivity earlier by looking at their reactions with water, their reactions with acid, and their reactions with salt solutions. Thank you so much, Tiffany, you star. That was amazing. I'm going to form tridonium chloride and tifonium metal. Let's balance the equation, shall we? It's correct, because tridonium is more reactive than tifonium. We know this because Brian was giving off more bubbles in the acid. We knew this. We only tested this. How do you spell it? Wrong both times. Tridonium. Tridonium chloride and tifonium. I like that. They're fine. So, right, let's balance it. 1 tridonium, 1 tridonium. 1 tifonium, 1 tifonium. 3 chlorides, 2 that doesn't work. Common denominator is 6. That there, that there. Right, made a change. Start again. 1 tridonium, 3 tridoniums. Right, made a change. 3 tridoniums. 3 tridoniums, 3 tridoniums. 3 tridoniums, 3 tridoniums. 2 tifoniums. Oh, 2 tifoniums. Oh, 6 chlorides. 6 chlorides. I'm okay. Okay, so there's my balanced equation. We know that that's what's going to happen. We already decided this. But in reality, what's happening? In reality, the chloride ions are doing nothing. Let me show you it in terms of my activity. So, click on that one, activity 1. Right, let's add a more reactive metal to these solutions. Let's add zinc. Right, and I'm click on molecular scale, zinc. I have no idea how to make that work. Zinc. Click here to place them in molecular scale. Start. Oh no. Use your mouse to drag the metal. Oh. I don't know why. It says I need a mouse. Oh, it needs a mouse. Hang on. Hang on a tick. Hang on. I want to show you this on a molecular level. It's just a nice animation, this. Let's see if my keyboard decides to wake up. It does. Right. Start. Oh, there we go. Step by step. Start. So the silver ions so the silver ions that are in solution. Let's go to previous. I don't like the hang on a minute. Let's start that again. Wait. Why are they in? Don't know why. By the way, they're not really meant to be in pairs. They're not there. They look like they're in pairs, but they're not. I know I don't like the animation. I'm critiquing my animation. Let's change that. Let's put that one back. Can't put it back. Let's put zinc into copper sulfate. No, reset. Zinc into copper sulfate. Start. Right, hopefully they're not in ions. Yeah, look at that. So the zinc ion, the copper ions land onto the zinc metal and they collect the electrons. So the chloride ions actually aren't doing anything. So we can look at it purely from a metal ion perspective. What we can say is happening is this. What we can say is that the tadonium is going from TO neutral and it is becoming TO2 plus. It is losing 2 electrons. Now, students often say, how have you just done that? How is it that you know that that's happening? Now, that's actually quite tricky because what I'm having to do is number one, I recognize that tadonium here is metal, which means it has a charge of 0. It owns all of its own electrons. It has no charge, 0 charge. But over here, it's bound to chlorine. So it's become tadonium chloride, and it's bound to 2 of them. And each chloride is -1, which means tadonium must be +2. That's what's happened here. So it's lost 2 electrons in that reaction. What's happened in terms of tifonium? Tifonium has started off as tifonium +3. So tifonium 3+, and it has gained electrons tifonium metal, and it has gained 3 of them. So we get two what are called half equations. A half equation is an equation showing reaction with one reagent, one species, in terms of whether it's losing or gaining electrons. I know that sounds really hard and complicated. You never get asked for that definition, by the way. You simply say that you're writing an equation with ions showing what's happening in terms of electrons. That's it. So in this case, these ones are being spat out. So which one's losing? Oxidation is loss. That's oxidation. Tifonium is gaining. So that's red. So we can now look at this from a redox perspective. Now, can I just say, at this point, I'm gonna step away from this and go immediately to questions. I've been ranting now for an hour, and it's definitely now worthwhile me looking at some exam-style questions to show you how this now relates. So let's do that. This is now kind of the end of the webinar. I thought I always like to bring exam-style questions with me because the exam-style questions make things a whole lot more straightforward. I don't know quite why they're not showing up. My laptop is having a small hissy fit. I don't know where they are. Where are you? The questions are there. They're just deciding to hide. Oh, there we go. Right. Let's zoom into there. Right. Question number 1. Oh, come on. My laptop is really struggling. That's probably because I'm running so many different things all at once. It's very much decided to have a bit of a hissy fit at this point. Hang on a minute. Oh, it's crashed. There we go. Right. So this question is about the planet Venus, which I think is very interesting. They're putting in a lovely context of space travel. So it says, although Venus is similar to Earth, it's very different in other ways. The temperature on the surface of Venus is 470 degrees Celsius. The atmosphere pressure is 90 times that of Earth. The clouds in the atmosphere of Venus are made up of droplets of sulfuric acid. Well, that's not good. The table of the list shows the metals that could be used to make a space probe to land on Venus. Right. Well, okay. First thing is, can we use copper? Well, it'll certainly survive. So copper would certainly, let's delete that because it's a bit dark. It'll certainly survive. It'll survive in terms of the acid because there shows no reaction, and it will also survive in terms of the melting point. But it's relatively dense. It's quite heavy. Let's look at the next one. Lead will survive on that, but it won't survive on the temperature. Bad news. We can't use lead. Let's look at magnesium. Can't use magnesium because it reacts with sulfuric acid, so that'll be eaten by the atmosphere. Its melting point, it would have survived on the surface in terms of melting point, but it would have reacted with the sulfuric acid atmosphere. Can we use nickel? Nickel's not a good choice. It's going to react with the sulfuric acid atmosphere. It would have survived on the melting point front. It would have not melted. And it's still quite dense. Titanium will survive on the atmosphere, will survive on the melting point, and has quite a low density, so it's going to be relatively cheap to put into space. Zinc definitely won't qualify. For either, in fact, I don't think. Yeah, it doesn't look like it. It's going to be close on the melting point. Okay, so the question number 1. Use this information. Which metal in the table could be used to make a probe with the lowest density? The answer is titanium. We can't use any of the ones. So what options do we have? We could either make it out of copper metal, or we can make it out of titanium. Those are the only 2 choices we've got. The reason being is otherwise they're going to be damaged in some respect, which is not going to be suitable. Why would this metal be unsuitable for making a probe? Oh, why would this metal be unsuitable? Oh, hang on a minute. I've made a mistake, haven't we? It says, which one can we use to make with the lowest density probe? The lowest density is magnesium. So that's actually going to be the probe with the lowest density, the lightest. And they're now then saying, why can't we use this? And the answer is, well, we can't use it because my laptop is really struggling. I need to close down all of these other apps that are running in the background. Let's see if I can close these down. Let's get rid of all these. There we go. So why would this probe, it's still, oh, there we go. Why would this probe not be suitable or unsuitable for landing? And that, of course, is because it's really struggling. My laptop's really struggling. So magnesium won't do because it's going to react with the atmosphere. Not suitable. I'm trying to move it down, and it's really not liking it very much. It's really, really struggling. Let's go to the next. Sorry, hang on. Oh, really struggling. Don't know why. If I zoom out a little bit, I think it might. Let's see if I can zoom out. If I zoom out, it'll be slightly easier. There we go. So, see if I can zoom in a little bit. Right. Very small amounts of lead can be used in electrical circuits. Why would lead not be suitable for use in electrical probes on Venus? Because it's going to melt. At that temperature, it's going to melt. Choose a metal from the table that would be most suitable for making a probe and give 2 reasons why. So the metal is going to be titanium. It has the lowest density of the 2 metals that won't react with the atmosphere and won't melt. So melting, you'd say titanium. Why? Reason number 1 is it won't react with the atmosphere. Reason number 2 is that it has a high enough melting point to survive with the temperature. Done. Right, next one. State why the reaction in stage 1 is described as a reduction. Right, now this is a great question. This is the first real GCSE one that we're now seeing. Let's have a quick look. There it is. So stage 1, let's see if I can make this work. Stage 1 is here, and it says, why is it described as a reduction? Well, in reality, the reaction is a redox, but we are extracting a metal, so we tend to call it a reduction. But what they want me to say is it's a reduction because nickel oxide is losing oxygen to become nickel metal. Done. So it's a reduction because nickel oxide is losing oxygen metal. That's what they want us to say. Next one, of course, is not to do with reactivity. Let's go to this one. Right. Okay, question number 2. I'm still struggling, still not responding very well to my movements up and down, struggling with it. Question number 3. This question is about the reactivity of some metals and their compounds. Right, state 2 properties of a metal that a student should keep the same in all the experiments to compare their reactivities. Right, and this is important, guys, because the students struggle with these questions. 2 properties of the metal the student should keep the same. Properties of the metal. Right, well, when we were doing our comparisons, we were doing our little ribbons. So what properties of our metal should we keep the same? We need to keep same surface area. That would be a reasonable one. Not, by the way, very difficult to control. Same mass of metal. Now, the problem is with that, I'm never into, when you're doing these reactions, the same mass of metal, we certainly need the same concentration of acid, same surface area. What I'm going to be saying is not the mass, but the same moles. That is a year 11 one, not for year 10s. We haven't done moles yet. But we need the same moles of metal. That would be far better. We'll look at that answer on the mark scheme in a minute. In fact, I think we ought to look at that immediately. Surface area and same moles. I think they'd probably allow mass. But let's check the mark scheme immediately for that one. There we go. Keep the same. Oh, no, hang on a minute. There we go. Amount in moles. Note, except mass or weight. So they actually allowed it. State of substance area, total surface area, particle size. So there we go. So those are our things we give them the same. It's nice to always go straight to a mark and check that we're getting it right. Reinforcement of information, of good data. Next, which is the least reactive metal? Right, what are they doing? Observations with sulfuric acid. Right, bubbles, no change, bubbles very quickly, bubbles form quickly. Right, so most reactive, second most reactive, third most reactive, fourth most reactive. So least. So it goes S-U-R-T. S-U-R-T. Which is the least, S-U-R-T. T is going to be the least. Which gas forms during the reactions with, so that's going to be hydrogen gas. We're done. Not for year 11, not for year 10s. This isn't reactivity now. This is just chemical tests making an appearance. Name the substance right. So we now say a student carries out an investigation of 4 metals. He adds to aqueous solutions of the nitrates of each metal. After a few minutes, he removes the strips of zinc and examines them. Name the substance that causes the brown coating on the zinc. Brown coating. So let's spot the brown coating. Brown coating. It's going to be forming copper metal. There's my answer. State why there is no change in the experiment with zinc nitrate. Oh, well, we were adding zinc metal to zinc nitrate. There's going to be no reaction taking place between zinc metal and the zinc salt solution. So there's no reaction taking place, therefore you're not going to see any change. Next, the student repeats the experiment with strips of metal M instead of metals of zinc. The table is shown below. So they're doing something similar to what I did before. Using the information, place the metal aluminium, copper, zinc, M in order of reactivity, decreasing down. So we have got, at this point, my laptop's paused again. I don't know why. If I adjust the zoom, it suddenly allows me to move it. It's very strange. So let's just check this. Draw. So we've got aluminium. This is aluminium and zinc, and there was no reaction. So aluminium must be above zinc. Next, we have zinc and copper. Oh, there was a brown coating. The zinc must be above the copper. Zinc nitrate, no reaction because zinc with itself won't do anything. Metal M, a gray coating of zinc. Right, so he's added zinc metal to metal M, and zinc has been made. M is more reactive than zinc. And we're done. What about, but now we need to check with the aluminium. There we go, look. No change with the aluminium nitrate because M could have been here or it could have been there. So we needed a second reaction to decide that, and there was no reaction of M with aluminium nitrate. So there's our order. Next, state why the reaction is described as a redox. Right, 1 mark. Magnesium is losing electrons. Losing, I shouldn't do that. Zoom in, right in. So this is, by the way, I'm trying to write on my tablet. This is losing electrons because it's becoming positive. So hang on a minute. That's losing electrons. Oxidation is loss. So Mg, that's going through oxidation. Blue, so we would say magnesium metal is going through oxidation because it is losing electrons. Lose electrons. What's happening to silver? Silver starts off positive and ends up going to silver metal. It's gaining electrons. Gain electrons. So that's going through red. Gain. So you would say in that answer, magnesium loses electrons and the silver 1+ gains electrons. Therefore, it's a redox because both are happening at the same reaction, in the same reaction. Explain in terms of electrons which species behavior is an oxidizing agent. Right. A police agent is someone who is enforcing the police. An oxidizing agent is someone who is causing oxidation. Who is being oxidized? Oxidation is loss. Magnesium is being oxidized. Yeah? So the agent is silver. It's hard, that. It's tricky. I'll go through that a bit more when we're in school. Next. Name a metal from the list that is extracted via electrolysis. Oh, anything above carbon. Carbon fits in there. That's clever that. They've taken lots of people out. Any of these guys are extracted by electrolysis. Observations, metals high in reactivity. I'm looking for one. That's the end of it in terms of mark scheme. So the important one there really, folks, is looking at these two. I just want to do one last thing. One more thing, which is when you have salt equations, if we had the Mg reacting with silver 1+, these reactions can be separated. Ag plus Mg 2+. Yeah, and it was balanced for you. Well, the reason why that balance happens is because if you look at the half equations, Ag plus is gaining 1 electron to form Ag metal. Magnesium is losing 2 electrons to form Mg 2+ and 2 electrons. We can put these 2 equations together. In order to do that, we need electrons to completely vanish. So we need to have 2 going in and 2 coming out. What that means is I'm going to double the top equation. If I double the top equation, then I have 2 electrons going in and 2 electrons coming out. I can now put those 2 reactions together. They cancel out because they're on opposite sides of the arrows. That's going in, that's coming out, so it cancels, and I get 2Ag plus Mg goes to 2Ag and Mg2 plus. And that was back to my original equation. So it's nice to kind of see that. Those exercises do need practicing, and I will give some more GCSE questions for you guys to practice. All right, folks? Well, apart from my laptop being a bit sticky, let's see if we can get my internet back up and running. Hey guys, thanks for coming. It's been an hour and 20 minutes. I'm sorry it's been so long. I will do my best to try and shorten it next time we have a webinar. But guys, have a nice rest of your evening. I hope it was useful. If you need any more help, give me a shout. It's been a pleasure to hang out with you guys for the evening. Take care. I hope it was useful. All right. See you guys.